to do with springs. And I had to, curiosity got the better of me, and he's English, unfortunately, but it would have been better if he'd been Scottish, but I'll live with that. And he has actually tons of different things. So this is just one of the things he discovered. So he's a real bright kid. And if you're interested in him, he was one of those like Renaissance people. He knew lots of stuff. He was an architect and did a lot of, after the Great Fire of London, he did a lot of stuff. So pretty interesting guy when you get to read about him. So let's talk about what this Hooke's law says. Essentially, it's to deal with the force and the work that you would use in moving a spring. And any spring has a natural length. So if you just left it alone, didn't pull it, it would be like, 6 inches long, right? Or 6 centimeters long. And then as you stretch it, it takes force to do that. And Hooke's law was a very simple formula. The force required to stretch it, X units beyond its natural length. So we don't measure X as the total distance of the spring. X is the extra bit you stretched it. So that's a little bit, you have to be careful of sometimes, right? X units beyond its natural length is given by this force function. The force to do X units is just K times X. K is a constant, right? It's a fixed number. And that depends on the material, right? So if you make the spring out of slinky wire, can you imagine K might be 0.0001? But if you made it out of some really tough steel, big, thick, suspension kind of steel, right? A big spring like that, can you imagine K could be in the hundreds, right? So every spring has a K value. And if you're told what the K value is, that's very helpful. Because then you can find the force. Now, of course, if you want to know what the work done, so the work done in stretching a spring, I'm just going to abbreviate it as X equals A to X equals B. In other words, A units beyond its natural length to B units beyond its natural length is given by the integral from A to B of the force function dx. So the integral that you have to integrate is always going to be K times X. So it doesn't change. What might be one question, it's nothing 0.2x, and the next question it's 42x, right? That's about the major difference. The constant may change. Any questions so far, or are we okay with that? Right, it's a bit like a physics class, right? So we are going to get questions involving springs, and we are going to figure out, well, what the answer is to each problem as it occurs. So I'm trying to find my first one. Oh, and something I should have mentioned, and I haven't. Units are very important. I know if you do chemistry, and I'm sure if you do physics, don't they always say units, units, units? Right? You can't have something in meters and something in centimeters. Everything has to be meters, right? So when you do these questions, make sure that you use meters and feet, depending on the story, and kilograms and pounds, depending on the story. And the kilograms and pounds don't seem to worry too much, but a lot of questions don't tell you meters. They tell you 42 centimeters, and they don't tell you feet, they tell you 9 inches. So don't use those numbers, turn them into feet or meters, depending on the context. So that's one question, that's one place where it's dead easy to forget, and you kind of lose the place here. Now, let's start with a version of Hooke's law. This is a version of question 5. And according to this question, it takes a force of 12 pounds to move a spring. I think they call it hold, but I've written down move a spring 4 inches beyond its natural length. And then the second part of this puzzle, the question really, how much work is done? I'll just call it how much is W. When it stretched 18 inches beyond its natural length. So there's really two pieces to this. The first part is actually just giving you enough information. In fact, this piece is going to be how we find out what K is. Now, once we know what K is, we can do this. How much work would it do to do this stretch or that stretch? So let's use this information here. Now, I know that the force function is K times X. In this case, the force is 12 and X is 4 inches. But I'm not going to use 4 inches, am I? What units will I use? Well, I have to use feet. So won't 4 inches be that guy? You happy about 4 inches being 1/3 of a foot? I just wrote down what the fraction is. So we have 12 equals 1/3 K. And as long as you do it to both sides, it's okay. So K is 36. That means we now know the force function for this spring. Because once you find out what K is, it's the same K forever for that spring. So in this particular question, K is quite a big number. 36 is quite a large K value. Now, we haven't answered the question, but we needed to get this fella to get to here. So when it says how much work is done, it's going to be the integral from A to B of K times X dx. So it's going to be the integral. Well, let's see. How much work is done is stretching 18 inches beyond its natural length. So it starts off at 0, that's its natural length, and 18 inches, well, isn't that 1.5 feet? 18 inches. So I'm going to call that 3/2. Kx dx. So far, so good. Right, now, next bit's messy rather than anything else. It's 18x squared. And it's going to be x equals 0 to x equals 1.5. And I am going to break one of my rules. But that's going to happen a lot in these questions. Because this is a physics question, decimals are going to be your go-to guy. So things really are going to be written down in decimal form. I prefer they weren't, but I'm not in charge of what people in physics do. So they like decimals, they get decimals. So what's that going to be? 18 times 1.5 squared, take away a load of nothings. I think this one's actually going to be okay. 18 times 1.5 squared. Okay, I get 40.5. And the units, you don't need to worry about them because they're in the answer, but they're foot-pounds. That's a pretty standard Hooke's law question. In fact, that's considered one of the simplest type, right? So you'll be given some information that allows you to get the K. And then once you know K, they'll ask you about how much work is done in stretching the spring. Now, in this case, it was 18 inches beyond its natural length. Can we pretend that it went and asked this question instead? How much is the work done when it's stretched from 4 inches, write it once, to 12 inches beyond its natural thing. Right, if you were being asked to do that, wouldn't there only be one minor change to our calculation? Right, this would still be 36. But suppose we wanted to know how much work is done in stretching it from 4 inches to 12 inches. Wouldn't our integral now be 4 inches, which is what, a third of a foot, and 12 inches, which is 1 feet, 36x dx. Do you see that the question doesn't really change much? Once you know what k is, you can find the work done in stretching it from anywhere to anywhere else, as long as you make sure you turn things into feet. Any questions about that? We good? Right. To me, it feels like a physics class, which I don't like physics that much, but whatever. Let's try another one. Let's do a version of 7 then. Okay, and this time it's going to take, no, take that back. I will do 7, but not that one. Let's do, it takes, I think of, it takes 50 newtons, there we go, force to stretch a spring 15 centimeters beyond its natural length. Then it's going to be how much work is done in stretching it spring from 30 centimeters to 40 centimeters beyond its natural length. So this is just basically a version of the same question we just finished. I'm just doing metric versions of it. Right, so this bit here, that's going to allow us to find k. So what do we know? We know that the force function is k times x. And the force here is 15 newtons. And it's going to be k times 15 centimeters. Danger. It's not going to be 15. What number does that 15 turn into? Metric conversion, 15 centimeters into meters.
It turns into 0.15 meters.
Right, and for those who are a bit rusty, don't you just divide by 100? Now, if you want to find k then, won't you divide both sides by 0.15? And 50 divided by 0.15 comes out to be 333 point lots of threes. And since this is a physics class, can you imagine you're just going to get ugly numbers? Because I've actually rounded that off to 1 decimal place. Now, the question, how much work is done in stretching it from 30 to 40? Well, the work done would be from 30 centimeters, which is 0.3 meters, to 0.4 meters of k times x, which is 333.3 x. Are you happy about that integral and where the numbers are coming from? Can you also see how ugly these questions are because of real numbers with physics people and you don't get 3 pi anymore, right? Can I just dot that because it's just going to be downright ugly calculation? Not a hard calculation, just ugly numbers. Right? Add 1 to the power, divide by the new power, plug in some guys, call it good. Now, in the 2 questions that I've given, we found K because they told us the force and the distance that it's moved, right? But there are other questions, other situations where that's not quite how it works. So here is question 7. Suppose it takes you 5 joules of work. So you're told the work. And you're also told that the spring has a natural length of 28 centimeters. And it takes 5 joules of work to stretch it from this 28 to 42 centimeters. And from this information, we can find K. Well, we have to be a little bit careful about what we're talking about here. The natural length is 28, so that's x equals 0. 42 is not 42. Isn't 42 how much more from 28 it is? So you see that guy is going to be a little bit trickier to get. So that's 2, that's 30, so that's 14 centimeters. Now, if that wasn't bad enough, don't we have to remember to use 0.14? Now, what do we know about work? The formula for work is the integral from A to B of the force function dx. And we're told that the work is 5. And so the integral from 0 to 0.14 kx dx. So far, so good, right? Somehow or other, we are going to figure out what K is, because we need to know K before we even think about moving on, right? We always have to figure out who K is. Now, you can see in this situation, it's a bit trickier than it was the last 2. But it is doable. Anybody any idea what I'm going to do next? So here's a puzzle. 5 equals this integral. What do you think I should do next?
Divide by 5.
I'm kind of thinking what you're thinking.
Subtract 5.
Not yet. I know what you're thinking. I think I know what you're thinking, but not yet. Let's focus on this guy. Do you know how to integrate kx? Well, you know how to integrate 5x, 10x, and nothing 0.2x, right? So you should be able to integrate kx. What is the antiderivative of kx?
K divided by 2x squared.
Are we all happy about the power rule? So you see what I'm doing here is I'm integrating this guy. Now you think, how's that going to help? Well, hang in there. That's basically a half k. So what are you going to get? You're going to get 1/2 k times 0.14 squared. Take away a whole load of nothings. So now we have 5 equals 1/2 k times 0.14 squared, which is 0.0196. And that in turn becomes 0.0098k. It's a physics thing, so ugly numbers are just going to happen. Right, now that we've got to this point, how do you get k?
You divide 5 by 0.009.
Right, can you see that these questions are just going to be ugly? Guess that's one of the reasons I don't like them. And I just realized they told me 2 decimal places, but I'm going to do that right now. 5 divided by 0.0098. And the answer looks like, wow, that's a big number. It looks like that. And that's 510.2 to 2 decimal places. Let me check that. Because it does seem kind of big. No, I'm happy with it. That is a massive spring. I mean, when K is in the hundreds, you're talking like, steel this thick springs. I don't know, the kind of springs that buildings do you know, there are buildings in California that have huge springs because of earthquakes. They're basically on a bed of springs. That's the kind of springs they're using here, right? That is massive springs. Okay. So sometimes you just got to trust the math, even if your gut feeling makes you go, oh, I don't like the size of that. Now, we haven't actually answered the question yet. Here are the 2 questions. I'll do one of them. It asks you how much to stretch it from 30 centimeters to 34 centimeters. And don't write this down because it's wrong. Oh, I know how this works. 30 centimeters, 34 centimeters. This horrible number. And integrate it. Seems reasonable, isn't it? What is wrong here? These numbers are actually not the right numbers. Shouldn't these numbers be how much beyond the natural length of the object, the spring? So 30 centimeters is actually just 2 centimeters more than 28. And isn't 34 centimeters 42, 28, 6 centimeters. So the work done is stretching it from 2 centimeters to 6. 2 is that tiny number, and 6 is that tiny number. 510.2x dx. Are you comfortable about why we had to change the start and finish values? Because the question just says stretch it from 30 to 34. It didn't say stretch it 30 centimeters beyond its natural length to 34 centimeters beyond its natural length. If they'd used that phrase, this would have been correct. It just said stretch it from 30 to 34. And because of that, we had to factor in the natural length value. So do you see there's a few places here where you can get caught out? Not turning things into meters will catch you. That's a common one with me. And sometimes not paying attention to the natural length. If you see a question and it mentions the natural length, you might want to be really extra careful in this. Now, this guy here is just ugly, but doable. Now, question B is a real puzzle one. And it says, how far beyond its natural length and they want the answer in centimeters, will a force of 45 newtons keep the spring stretched. Now I have our force function. It's 510.2x. You tell me the force is 45. If you divide both sides by this horrible 510 guy, you get the answer 0.0, what do they want decimal places? 0.088 roughly. But that's meters. So doesn't that become 8.8 centimeters? Once you know what K is, can't you find questions like the work done? Can't you also do questions like how far is the spring going to be stretched for any given force acting on it? Right. Work done? How far you stretch? Okay, any questions about that? Because there's a lot going on in that one question. It's fraught with dangers. So one last time, will you remember to read the question carefully? Because sometimes 30 and 34 are the right numbers. And sometimes you have to take into account the natural length. So if it says 30 centimeters beyond its natural length to 34 centimeters beyond its natural length, use this guy. If it just says stretch it from 30 to 34, somewhere you'll be told the natural length and you have to factor that in. I'm going to move on now if there's no more questions. God, this feels like a physics class. I want to get back to doing cool stuff. Okay. Diversion question 8. Now, it's very similar to the one I've just done, so I'll give you the gist of it. It takes 5 joules of work, and I think I've just done that one, haven't I? Yeah, I'm not doing that. Question A is just basically a carbon copy, question 7. It just happens to have different numbers in it. Okay, so let's look at 9 then. Oh, good, different units. Work required to stretch a spring 1 foot beyond its natural length to 6 feet beyond its natural length. If the work required to stretch a spring 1 foot beyond its natural length is 6 foot, okay, so the work done is 6 foot-pounds, and it's going to stretch it 1 foot beyond its natural length. So you're doing from 0 to 1. Okay. If I tell you it takes 6 foot-pounds of work to stretch it 1 foot, would you agree that's the formula? Right, work 6 from beginning to 1 foot beyond its natural length. Integrate. Evaluate at x equals 0 to x equals 1. Well, this one's coming out far too nice. So K ends up being 12. That's fine. So that's our go-to force function. And it then asks you how much is needed to stretch it 6 inches beyond its natural length. So they want to know the work done 6 inches beyond its natural length. Okay, what would the integral look like to calculate the work done in stretching it 6 inches beyond its natural length? What would the integral look like?
It would be the integral from 0 to 0.5.
Great. Power force function dx. Would you agree that that's pretty boring? I mean, aren't these just going to be versions of x squareds, right? Power rule, add 1 to the power, divide by the new, and then plug in this case 0 and 0.5, and get some ugly decimal, and that would be it. Okay, we got one last one of these guys, and then we get to actually some kind of, well, I think are fun questions. I'm not so keen on spring questions, but the ones that come after, I do like them. According to Hooke's law, we already know about that, so I won't read that out to you. This time, it's going to take you 2.4 joules of work. And it's going to take, that's how much it takes to go from 13 centimeters to 17 centimeters. And then it takes another 4. What's that doing there? What is that doing there? Oh, I don't need to do this one. My apologies. No, you don't need that one. Forget about 10, it's not going to be there. I will kill it later. And the reason I'm kicking it out is because it involves a system of equations, because you have to do it twice just to solve for k. And I don't think we need to do anything as messy as that. That's not really what I was expecting. So we're now on the last topic, and that is work done in pulling things up cliffs. I love these puzzles. So we've done all the spring stuff. Don't worry about 10, it'll have disappeared by the time you get to look at it. So it won't be there. So what are these guys going to look like? Well, imagine that you've got a cliff. Sometimes it's a cliff, sometimes it's a building, sometimes it's a tree, but you've got some vertical object. And at the top of this object, you've got a guy. And this guy has a rope. And I'm going to tell you that the height from the top to the bottom is 200 feet. And since this particular rope reaches the ground, that means this story, the rope is also 200 feet. But sometimes he's only got the rope and it's dangling halfway, right? That doesn't change too much. And I'm also going to tell you something about the rope. The rope weighs 0.2 pounds per foot. And sometimes the rope is called a chain, but it doesn't change the story either. And we are going to figure out how much work is done in pulling that rope to the top of the cliff. Now, that's not as obvious as you think. You might just say, well, it's 200 feet and it weighs that much. So if I just multiply these two together, I get 40, so it must use 40 foot-pounds of work. Right? Seem reasonable? Also wrong. If you just multiply this distance by that weight, you are not actually calculating the work. That would be the work done if the rope was in a big pile at the bottom and you climbed to the top of the cliff with it. Can you imagine as you pull this rope up, doesn't the amount of rope that you're pulling against get lighter because there's less of it? Can you imagine the last foot, having you only got 1 foot of rope? What's that? 0.2 pounds, right? And at the beginning, don't you have 40 pounds worth of rope? So you see how this is quite a complex issue. We don't have a fixed weight for the entire journey, don't we? Doesn't it keep changing? So we are going to show you a really cool trick. First thing I'm going to do is describe a part of the journey. I want you to imagine that we're here in this journey. X units above the top of the cliff, right? I'm going to call that distance X, right? And what we're going to do is we're going to calculate the force function. And the force function is simply just the weight of the rope at that point. So we are going to figure out what the weight of the rope is at position X. Okay. If that's X feet, how much does the rope weigh if you've got X feet of rope?
It weighs 0.2x pound.
Agreed. Agreed, 0.2x. Now, don't we have a formula for calculating the work done? And isn't the work done the integral from the start to the finish, right? From where the thing started to where the thing finishes? Force function. Still with me? Now, we have just figured out the force function. What we have to figure out now is what's X at 0, or I almost said the answer there. What is the values of X at the start and the finish of this journey? What will X be when you reach the top, and what's X going to be when it starts off the bottom? I guess that's what I'm trying to say. Start and finish value for the rope.
Would it be the integral from 0 to 200 feet?
Correct. Why?
Because I was thinking of it as position X is the very end of the rope.
Right.
Starting at 0 feet, and then you're ending at 200 feet.
Right. So would you agree that in this journey, X starts at 0 and it finishes at 200? Would that kind of make sense? Right. So we now we solved a problem. How much work is involved in pulling this 200-foot rope from the bottom to the top? And one of the reasons I love this question is it doesn't have any kind of need to do it. I love questions that are just pointless. I just love them for the puzzle feature. Side issue. The branches of math that I love the most are the ones that nobody has found a use for them. So, and the minute engineers and science people start playing about with it, like the spring questions, I lose interest very quickly, because what happens is the numbers get really ugly and it just becomes a kind of number crunching process. But these guys, I guess you might want to know how much work is pulling a rope up, but would you be honest, it's not something you would really be that interested in. But it's cool regardless. Add 1 to the power, divide by the new power. And we get 0.1 times 200 squared. Take away a whole load of nothings. And we'll stick to the decimal rule, because this is basically what we've got to deal with. We end up with 4,000, and the units are feet and pounds, so it's foot pounds. Now, if I put this fella over here because I used too big a picture for Mullen Good. And the answer to this was 4,000, right? That's fine. Now, 200 feet. Do you think pulling it halfway is going to require the same amount of work for the first half as the second half? Do you think it's going to be an even split? In other words, if you only want to pull it up to the 100-foot mark, it's going to cost you, what, 2,000 foot-pounds, and then the other half is going to cost you another 2,000. Or do you think those may be different? Okay, nod on different. What's the logic behind why the two answers are going to be different? Because we're going to calculate them in a few seconds. What's the logic? Why is it harder to pull the first 100 feet than it is to pull it up the last 100 feet?
Is it because of the gravitational force?
Yeah, isn't there more rope so that, you know, it's working on a heavier rope? Isn't there more rope in the first 100 feet than in the last 100 feet? Right. Now, the integral for those two would be going from 0 to 100 feet, right? That would take you halfway. And wouldn't 100 to 200, wouldn't that take the other half? Agreed? 0, 100. Now, the formula doesn't change. It's still 0.2x dx. And the integral of it is still 0.1x squared. In this case, got to be quick here, we're almost out of time, to here. And this one, it's 0.1x squared, and it goes from here to here. Before I actually start hitting buttons in my calculator, you know that one of them is going to be bigger than the other? Do you think it's going to be just a little bit bigger, twice as big, a lot bigger? What's your gut feeling?
It's going to be a lot bigger, isn't it?
I would think so. Let's see what's going to happen. So in this case, it's going to be 0.1 times 100 squared, take away the whole of the nothing. So I'll do that one first. 0.1 times 100 squared. Oh, it's going to cost that much. And this fella, well, he's going to be 0.1 times 200 squared minus 0.1 times 100 squared. So 0.1 times 200 squared, subtract 0.1 times 100 squared. And I didn't need to calculate that at all. How come I knew that that was going to be 3,000 before I even did this?
Because the only thing that changed was the 100 to 200, and squaring that gives you 4,000 instead of 1,000.
Well, it was true. I was just thinking, if I know this is 1,000 and I already know the total is 4, isn't the other part of the story what's left? Do you notice that the distribution here is actually 3 times as much work? Right? That's the first half. Sorry, that's the top half, right? And that's the first half, the bottom half. That seemed reasonable. Have you noticed with very little work in calculus, haven't we been able to model quite a dynamic situations? You know, that rope's not the same weight all the time, right? As you pull it up, it keeps changing weight, right? So the amount of work you're doing keeps changing. Yet the formula for calculating it ended up being tiny, right? A very simple formula. That is the power of calculus. Can you imagine how hard that question would have been before Newton did calculus? I mean, I'm not even sure where you would start. Well, this seems to be a very good point or a very good place for us to finish.